Besides algebra, the other thing I want to review before we really get into the calculus are functions. As we go through this review, you'll notice I'm kind of stretching it. There's going to be definitely some new things. Make a note of them. If you don't know them, it's okay. We're going to learn them throughout the calculus course, but I always like to throw things at you early just so we can start thinking about them. Okay, so function notation. We used to have equations and they'd be happy and they'd be like y equals 3x plus 7. And then at one point, I think it was in the graphing unit, we started talking about function notation, where instead of using the variable y, we would use f of x. And we say that just represents saying that, whatever is a function of x. It could be g of x, if you have multiple ones, h of x. You could put any variable in front of the x, but that makes it a function notation. Okay, a new concept, maybe, are the domain and range of a function. Domain deals with x, and it's what values of x can this function be. So let's look down here at this linear function here. How do I know it's a function? It passes the vertical line test. There's only one y value for any particular x value. So looking at this, what values can x be? That line is going to go on forever in either direction. So x can be anything and still have a value on this function. So when that happens, we say that x is an element of the real. And this is the symbols for it. Now, I don't really care, I don't think, if you know that, but just to know if I say that in class or where that comes from, I'm saying x is an element of a real. That just means x can be anything. X can be any real number. The range are the values of y that your function can have. Looking at our first one, again, just like x can be any number, y could be any number. So y is also an element of the real here. And this will be true of any linear equation. X can always be anything, y can be anything, unless we've got some other restriction in there that we'll get into as we calculus. Let's move to the second graph, our parabola. What can x be? Well, it's hard to see, but as you go further and further up in the positive y direction, that's going to keep going forever in the negative x and positive x direction. So once again, for this parabola, x can be anything. Y is a little different because we have a minimum in this case. Like this graph will never appear below this point right here. So if we're talking about y, we're going to say that y is greater than or equal to negative 2. That is the range of y. The range of x is x element of the real. Moving over to our third graph, which is a cubic. It has some like maximums and minimums, but they're local, right? The graph is going on either end, up and down, right? So it does a little blip in the middle, but it still doesn't change the end behavior of this graph. We'll talk about that later too. So I look at this and I'm like, yeah, x could be anything. It may take a while to get there, but it's going to continue going to the left and the right indefinitely. And same as that, y is an element of the real. So that's the domain and range. The domain is what x can be, and the range is what y can be. So we'll start with linear functions. And the most basic equation for a linear function would be, oops, let's not do y, let's do f of x. F of x equals x. So key features, if you have a variable, the exponent is 1, which means you don't see it. So x squared is not a linear function. The graph is always a straight line. And we usually like to write it in what we call slope-intercept form. Y equals mx plus b. So this is adding on a bit of stuff, where m is equal to the slope, which we can find by counting on a graph or using math, y2 minus y1 over x2 minus x1, which is the same as saying the change in y over the change of x. And b, and some people, they just don't get this, but b is always going to be your y-intercept. So it's not y coordinate, It's this point where your graph, where your line, wherever it might be, crosses the y-axis. So if I look at the one we've got on the graph here, f of x is equal to mx plus b. How can I figure out the equation of this graph? Well, I see that b is 3, so I know already that f of x is equal to mx plus 3. If I'm given the graph, I can determine the slope by counting. So find another pretty point. I like this one over here. I know there's another one, but it's too obvious. And you can count. So how far did I travel? What was my run? That's a horizontal travel. I had 4. What was my rise? I went from 3 to 4. That was 1. So rise over run, change in y over change in x gives me my slope. So m will be equal to 1 over 4. Up 1 over 4. So I know the equation of this line is 1 over 4x plus 3. And now I can find what f of x will be at any x value. I can pick anything I want. So let's say I'm lazy and I pick -4. I want to know what y is when x is -4. You just substitute in -4 for x and see what the graph will spit out for you, or the equation rather, and you're going to get -1 plus 3 equals 2. And sure enough, there's that point on the graph. You can also use your slope formula to find the slope from 2 points, and that works well when you don't have a picture in front of you. So let's go check that out. Here we go. Find the equation of a line passing through the points -2, 3, and 4, 1. So we have 2 points. I'm not great with x and y. I tend to flip them, so whenever I do these questions, I always label my points so that I put things in the right place. Because the first thing I'm going to find, I need to get this going, but I don't really know m, and I definitely don't know b at this point. So I need to find those. I'm going to start by finding the slope. And I'll use my slope formula. Change in y over change in x. And because I've labeled them, hopefully I'll put everything in the right place. -1 minus 3 divided by 4 minus, and watch your signs, -2. That will give me -4 over +6, which I can reduce to -2 over 3. And we generally like to leave our slope as a fraction, especially since if I divide 2 by 3, it's going to make a disgusting decimal. So let's just leave it as a fraction. So what do I know so far? Y is equal to -2 over 3x plus b. So now I have to figure out what b is going to be. You can use either point to solve for this, just don't change things around. So maybe I will use 0.2. So I'm highlighting that. So make sure that's the x and the y that you insert into this equation. And what I'm going to do is I'm going to replace y with the -1 from that point. Whoops, with a highlighter apparently. With the -1 from that point. I already found the slope. And I'm going to replace x with the 4 from that point. And I'm going to solve for b. All right, let's take it up over here. -1 is equal to, and remember when you multiply a fraction by a whole, you're multiplying numerator, -8 over 3 plus b. I'm going to isolate b. I'm going to at the same time change -1 into a fraction over 3 because I know I'm going to be adding fractions. -3 over 3 is how you represent -1 as a fraction over 3. As I move this to the left side, it's going to become positive. And I'm going to end up with 5 over 3 equals b. So a lot of people walk away at this point. Remember the question was find the equation, so make sure you answer it. I'll answer it right up top. Y equals -2/3 x plus 5 over 3. Next up, we're going to look at quadratic functions. And the parent function for this graph, f of x, is equal to x squared, the most basic parabola you could have. Key features. The exponent is always 2. It makes a smiley or a frowny shape. it has symmetry about the center of the parabola. So every point at any given y is equidistant from what we call the axis of symmetry, this line we could draw right through it. So if I go from here to my axis of symmetry, this is the same distance as if I go from this side to my axis of symmetry. Other key points, the maximum or minimum is called the vertex. We have a y-intercept. It tends to be less exciting than it is when we're talking about lines, and then we will have 2 X-intercepts, or 1 or 0, depends on the parabola. And those X-intercepts can also be called roots or solutions, lots of names for these features of a parabola. So let's review the math. Here we have an equation and we want to find key points, so those key points are generally going to be vertex, the y-intercept, and the X-intercepts if they exist. Okay, so let's talk about the easy one first, the y-intercept from standard form. That means you're going to be crossing this line. When you cross the y-axis, x is 0. So really, if you're finding the y-intercept, you're finding f of 0. And there's a shortcut, but we'll do the long cut first. 3 times 0 squared, plus 4 times 0 minus 4 equals minus 4. So I know my y-intercept happens at this point right here. And that's always going to be true in standard form. Anything with an x is going to multiply to 0, so you can just look to the c value to get your y-intercept. If you want to find your x-intercepts, you want to find when you're crossing the x-axis, and when you cross the x-axis, you have the equation set to 0. Y will be 0. So I have 3x squared plus 4x minus 4. What can I do here to find it? I could factor whatever method you like. This is mine. Take the AC line, a times 3. 3 times negative 4 is negative 12. So I need factors that multiply to negative 12 but are 4 apart. I know that 6 and 2 would satisfy that. In order to make both equations work out, and I'm sorry, that is a B line, that 4. Both equations work out. One of them has to be negative. I'm going to make the 2 negative because 6 minus 2 is 4. I move on to the trick. So I've got a video if you don't know the trick. You can use decomposition, you can use whatever else method you have, and I find out that I can go to 0 equals x plus 2 onto 3x minus 2. Okay, so make sure you know how to factor still. All right, so we're looking at this bad Larry. What are the zeros? What are the things that make this true? If I have the binomial in green add up to 0, then 0 times the second binomial will be 0. So if I set x equal to negative 2, that would work out. If I set the binomial in yellow, so that would add up to 0, we're good there too. So if I had x equals to 2 over 3, the 3's would cancel, the 2 would drop down, 2 minus 2 is 0. So these are my x-intercepts. So one of them is pretty, negative 2. One of them is not so pretty, 2/3. So be it. Let's figure out the vertex. So we can use the vertex finder for that. What you do is you start by finding the axis of symmetry. You could use the 2 roots, add them together, divide by 2. You can also use this cheat formula, negative b divided by 2a, where b, let's pink it, is going to be 4, and a is going to be 3. So we're going to have negative 4 divided by 2 times 3. And we're going to get the axis of symmetry is happening at negative 4 over 6, which is the same as negative 2 over 3. So I have an axis of symmetry right along here. Now, remembering also that the vertex is equal to, the x value will be the axis of symmetry, so that negative 2, 3, and then whatever you get when you put that axis of symmetry into your equation. So I know already it's going to be negative 2/3, and I just have to insert negative 2/3 into my original equation over here and solve for solve for y. Good Lord. Hold on. Here we go. Taking that equation and we are looking for f of negative 2 over 3, that axis of symmetry. We're going to have 3 times negative 2 over 3 squared plus 4 times negative 2 over 3, I'm running out of room, minus 4. So we're going to have 4 over 9 if we square that fraction, and then if we multiply it by 3, we'll end up with 4 over 3. I can cancel 1. Minus 8 over 3 for the second term, and then we have that minus 4. I'm going to change that into a fraction over 3. Negative 4 is equal to negative 12 over 3, just so I can do the math. So I have 4 minus 8 minus 12 is going to give me negative 16 over 3. So my vertex is going to happen at negative 16 over 3 in the y direction, negative 2 over 3 in the x. So we had that axis of symmetry, continue it down. 16 over 3 is like 5 1/3. So let's say the vertex happens right about there. And here it is. And here we go with another quick look at our trig graphs, sine and cosine. And once again, if this is unfamiliar to you, go back to your level 1 teacher's resources or go to my YouTube level 1 resources. I've taught the course you took before this, so you can find it there. I know it's quick, but hopefully it comes back quickly. All right, so we'll talk about sine first. Sine is like a measure of y. The graph of sine would start at 0, go to a maximum of 1 at 90 degrees or pi over 2. So remember, radians are back. Definitely going to want to work with those. We go back down to 0 at pi or 180, a minimum at 270, 3 pi over 2, and back to where we started at 360. So this is the period right here. And for this particular sine graph, the period is 360 degrees or 2 pi. That's a time to get through one cycle. Other key features of this graph, I'm just thinking, amplitude is between a maximum and the center line, or the minimum and a center line. Here's another amplitude. So we can go a little a, symbol for a, and that, if you have a graph that's not the parent graph, not just y equals sine x or f of x equals cos x, your a shows up here as a multiplier in front to change that amplitude. Cosine is like a measure of x, and it starts at a maximum and goes through 0 down to negative 1 at pi, and then finally back up to a maximum by the time you get back to 360. Okay, so just remembering cos, one cycle looks like this, sine, one cycle is a Loch Ness monster. And if you had a negative sine graph, what would it look like? It would just flip, spin around that axis. Negative cosine would look like that. We're headed into new territory now, and I just want to talk about higher degree polynomial graphs. So not y equals x, not y equals x squared, but onward to x cubed and upward. Okay, and how you can recognize, you can't always tell like what graph you're looking at, but you can hazard a pretty good guess just by the shape of that graph. So I'm going to start by looking at number 1 here. Okay, and I see that it comes up from negative and heads up to positive. If a graph has that shape, I know that it has to be x to the power of an odd exponent. Okay, so it could be x cubed, x5, x7. This is what x to an odd exponent would look like. The second one here is kind of the same, but it's kind of wonked and going the other way. This just means this graph is negative x. So there's that kind of flipping of the parabola, or flipping of whatever. You flip an odd exponent graph, this is what happens. Negative x to an odd exponent. I don't even know what that looks like. Looking at number 3, like a parabola goes up on either end, it's smiling and happy. This graph eventually does it as well. It has some wonky stuff going on in the middle, but both of the ends of it are pointing upward. This is a graph to some sort of even exponent. I know it's not x squared because I know x squared always makes a parabola, but it could be x to the power of 4, x to the power of 6, so on and so forth. And our last polynomial graph here, with both pieces pointing downwards, is just a reflected graph. So that would be negative x to an even exponent. So just a little bit of a heads up. There's going to be lots of graphs in this course. Sometimes it helps if you know a little bit beforehand. There's also a lot of terminology for graphs, so let's go through some of them. And once again, you'll see these later, but let's maybe kind of get them in our head now. The first thing I want to talk about are intervals of increase. So where is this graph going up as you head from left to right? And we're going to speak in terms of x. So I can just take a highlighter and be like, okay, if I follow this graph with my finger, I'm going up, I'm going up, I'm going up. Then I start going down. So that's an interval of increase, and it stops right there. But I see that happens again from this point up. So if I want to think about my intervals of increase, it looks like it's going to be x is less than, oh, I don't even know what that is. Let's call it negative 1.5. It's probably not. Who picked this graph? And then x is greater than 0. That's when that graph is increasing. What's our interval of decrease? Well, I only see one chunk. I don't know if I want to use this color. I'm going to mark that this is this one, mark that increase was yellow. And that's kind of trapped between those two values I had. So x is greater than negative 1.5, but less than 0. So getting used to that kind of notation, how to describe intervals. I don't need you to tell me what the y value is or f of x is at that point. That's fine. All right, local maxima. Where do you have the top of the hill happen? Right here, okay? And that happens at that x equals negative 1.5. Let's go to another color for our local minima. When do you have the bottom of the valley? One happens right here, when x equals 0. When I think about concavity, concave up means you're opening up, you're smiling. Concave down means you're frowning. So where is this graph? Well, let's start with concave up. And I'm trying to think of how I'm going to represent that now. Give it a pink. If we go to our x is negative 1.5, from then on in, it kind of looks like it's making a smile at that point. Likewise, if I look about where the graph is frowning, it looks like it's happening from, way over here down to this point. Now, the problem is with that, you can't have this part happen. You can't be both concave up and concave down. So somewhere along this blue part, we switched from concave down to concave up, and we call that the turning or the inflection point. So I'm going to eyeball it as right here. So to be fair, and I'm just going to quickly erase, you would have to kind of take off this section of your concave down and take off this section of your concave up. And this point where you're switching is your turning point. Let's try and assign a value to that. So we see that we're concave down from basically negative infinity, let's say, until we get to, what are we going to call that? Oh, let's call that negative 2/3. Let's go with that again. So the beauty of the graph, that's why we have calculus, so we can actually get a number instead of guessing. Okay, and we'll say that we're concave up from negative 2/3 all the way to positive infinity. Our turning or inflection point happens at x equals negative 2/3. When we speak about end behavior, we want to know what our graphs are doing as x approaches negative or positive infinity. So as we go off forever to the left or the right, what is our graph doing? So if we look at this pretty little cubic here, as x approaches infinity, what is f of x doing? Well, this is x going this way. Y is continuing to go up. So as x approaches infinity, y is also approaching infinity. This is, and when we look at the other end, as x approaches negative infinity, y also approaches negative infinity. This is a behavior you would see in your standard odd exponent graph that hasn't been reflected. So depending on the nature of the graph, this may or may not be true, what it's doing as x approaches negative or positive infinity. We've done a lot of math with rational expressions, but we haven't spent a lot of time with the graphs, mostly because they're crazy. So this is a graph of, actually I think it's not, I think it's 5 over x, but it could be the graph of 1 over x, which is the most basic of the rational expression graphs. It goes crazier from here. So just look at this bad Larry. What's going on? There seems to be certain values that x never reaches, right? Like it doesn't look like x is ever going to be equal to 0. Likewise, it doesn't look like y is ever going to be equal to 0. And I wonder why that is. I wonder what restriction I have and how that corresponds. So let's take it over to the math slide. Thinking back to the algebra review, whenever we were looking at rational expressions, we would kind of figure out the restrictions, which were things that the denominator could not be, because you'd make it equal to 0. So let's just do what we did last time, which is factor where we could. And if we do that, we get x minus 3, x plus 1. So before we do any canceling, you always list your restrictions. So x can't be 3, and x can't be 1, because either of those values would make the denominator equal to 0. Now, I noticed that I could cancel this, and I could express this equation as 1 over x minus 3. We're going to set that aside and go to the second equation, g of x. Do the same thing. I can factor the numerator this time. Before I do anything else, I list my restrictions. X cannot be equal to negative 2. But if I were to cancel that one, my equation becomes g of x is equal to x minus 2, a much simpler equation. So one of these things makes an asymptote, and that's the one where it stays in the denominator and it doesn't get canceled. One of these things is a whole, and that's the one where it canceled. And let's see what they look like on the graph. So we'll graph f of x in red. So what do I know? How am I going to graph this? Well, I know in the previous slide it looks like that wonky shape, so I could take that with me. But I know that I have a restriction. And I know it's an asymptote, which is a line that your graph cannot cross. So at x equals 3, I have a line, and that this graph will never appear at x equals 3. Before I do the second restriction, I'm going to try and sketch this bad Larry. X is never going to be equal to 3, therefore y is never going to be equal to 0, because there's no variable in the top. Not a great drawing, but that's the best I got. Now let's look to our second restriction. Our restriction was x could not be equal to negative 1, but it's not an asymptote, it's just a hole. So what does a hole look like? Take out the graph at that point, and I'm exaggerating this a bit. So at negative 1, x equals negative 1, I just have this little hole in my graph where it can't be. So you can trace along that graph happily, but at x equals negative 1, you're just going to hit a hole and have a discontinuity. So that is f of x. G of x is much easier. It just looks like a straight line graph. I see that the slope is 1. I see that the y-intercept is negative 2, so I'm going to start here, kind of put a couple points on so I at least get an approximately good line. There we go. And my restriction here was that x could not be negative 2. So I want another hole, and I want it to be right about where x is negative 2, x is negative 2 right there. So when you see a graph of a line with a hole in it, it probably just wasn't g of x equals x minus 2. It was probably a crazy rational expression that simplified. But once again, just laying some groundwork. Sometimes a function has to be described by several different equations at different x values. We call these functions piecewise functions, and they can be continuous, like the one on the top, or they can have jump discontinuities, like the one on the bottom. So how do I describe this graph? You just have to figure out what each part the equation would be. So when you write this, you would do, for the top one, you'd have f of x is equal to, and I see three very different things happening, so I know I'm going to have three intervals. If x is less than or equal to -1, then the equation would be 2x plus 4. And you can figure that out just by using your math skills. And I realize I should have written them in opposite order, so bear with me. That's a little better. Okay, so looking at the purple part, the second part, that's just y equal to 2. So f of x is equal to 2. What's the interval? If x is greater than or equal to -1, but less than or equal to 2. And my last interval starts here and can be described by the equation f of x is equal to -1 over 2 x plus 3. Just using 2 points on that graph to figure out the equation of that line. And that happens when x is greater than or equal to 2. So there's how you do a piecewise function. Let's look at our second one. Coming in, the red part is a parabola, and I see something a little different. I see some open circles and I see some closed circles. So what that means is that -1, it's defined on the red graph, the red part of the graph, but it's not defined. It has a hole on the purple part. So if I want to know what f of -1 is, I would look to this point. F of -1 is 2. It is not 4. Okay. So let's get going. That just means our greater than less than signs will be a little bit fancier. So you can either project that or you can do some math to figure out that that graph is still going to be 2x plus 4. I get lazy when I make these up. And my interval that is true for, I'm going to be more careful. X is less than or equal to, because of the closed circle, to -1. The second graph is a parabola. You can do, it looks like it goes over 1 up 4. It has a step pattern of 4. So I know that the a value is 4. And it hasn't been shifted left or right, so I'm just going to call it 4x squared. And I'm going to be careful. So that happens, starts at -1. So x would be greater than -1, but because of that hole, I can't put the little line underneath the alligator or the pizza or whatever. It will not be -1. It can only be greater than -1. However, it has a closed circle at the end of that section, so it can be equal to +1, where that graph ends. And now we're going on to the blue one. Do a little mathing. You're going to get -1/2 x plus 1 as the equation. And x is going to be greater than 1. It can't be equal to 1 because it's a hole. It's open at that. So there's a piecewise function with some discontinuities in it.